Dear students, in this video lecture we are going to discuss the timing diagrams of 8085 microprocessor. So before moving towards the timing diagrams of 8085, we will see the various operations performed in microprocessor where the two main things are need to consider. The first one is the instruction fetching and second one is the instruction execution. So these are the two things are need to consider during the execution or operation of any instruction in 8085 microprocessor. So about instruction fetching, where the microprocessor fetches the opcode from the memory to perform the operation. As we know, depending on the hexadecimal opcode, microprocessor takes the decision to perform a specific task. So during the execution or operation, first microprocessor fetches the opcode from the memory. So 8085 fetches the byte or operational code or opcode from the memory for the specific instruction. The first byte of any instruction, always remember, is opcode, which is fetched from the memory and get loaded in instruction register. So 8085 executes the special fetch cycle to fetch or to read the opcode from the memory, and this particular cycle is also known as the opcode fetch cycle. Then during the operation, next thing is the instruction execution. So after fetching the opcode from the memory, the execution of the instruction starts. So during this particular period, 8085 executes the fetch the instruction from the memory, and there are two types of executions are mainly observed in microprocessor. The first one is the internal execution or internal operation, where the two things are need to consider. The typical instruction format we have already discussed, which consists of the opcode and operand. The opcode field will give the information about the opcode of the instruction, and operand, in the operand field you will find the register, 16-bit or 8-bit data, or 16-bit or 8-bit address. So in case of internal execution or internal operation, when the operand is from internal register, so in the operand field, if suppose internal registers are there, so at that time internal execution is need to consider. For example, the instructions to perform arithmetic, logical, decision making instruction, data transfer kind of instructions and related operations. So arithmetic instruction, for example, add b. Okay, add b. So add b means accumulator content get added with b register. Okay, sub b, in front of sub b is there, so operand field consists of b register. The next type of execution is the external execution or external operation. If suppose in the operand field, if you find the 8-bit or 16-bit address related to memory operation, so at that time external execution or external operation is need to consider. So external execution when operand is from memory or IO module or IO port address. So memory read write kind of operations, IO read, IO write kind of operations are need to consider under this external execution or external operation. The memory related instruction like LDA C000. So LDA means load accumulator direct from memory address C000. So in the operand field, C000 means the address of the memory location. So this is about the various operations observed in 8085 microprocessor. Now we will move towards the timing diagram concept. So what is timing diagram? So timing diagram is a graphical representation. So it represents the execution time taken by the instruction during the execution in the graphical format. Also it shows the active signals during the operation or during the execution of the instruction. So various control signal, address lines, data lines, and the other signals, and the status of the other signals we can easily identify during the execution with the help of this, with the help of the timing diagram. So to understand the timing diagram and various signals which are observed in the timing diagram, we will see various signal representations. The first one is the clock signal. As we know, in 8085 all the operations get performed in coordination with the digital clock signal, and to generate digital clock signal, X1 and X2 two pins are given, where we are going to connect the crystal with 6 MHz value or RC or LC tuned circuit, and the external crystal frequency, for example 6 MHz, get internally get divided by 2, and due to this reason approximately we are getting the operating frequency, internal operating frequency 3 MHz. So minimum to maximum range of the 8085 microprocessor clock frequency you know very well. So this diagram represents the clock signal. So this is the practical clock signal which shows the rising edge and falling edge, or positive going edge and negative going edge with some rise time and fall time. So this is the practical clock signal where we are getting some rise time and fall time. So rise time and fall time, the time required to change the state from logic 0 to logic 1 or from logic 1 to logic 0. Okay, so here logic 1 is changing from logic 1 to logic 0, and this particular period is known as the falling time, and one complete cycle is known as 1 T state. Next signal representation, single line signals. So status of single line signal will be either logic 0 or logic 1, that is active low or active high. So signal requires some time to go from logic 0 to logic 1 or logic 1 to logic 0. That is, the signal requires some time to change the state, that is to go from logic low to logic high or from logic high to logic low. So in this figure we can able to see the two single line signals, where the first one is changing the state from logic 0 to logic 1, and second one is changing from logic 1 to logic 0. Then multiple line signals. As we know, 8085 microprocessor consists of multiple line signals. So if we combine all these signal, then the group of signals are known as the bus signals. So instead of showing the separate signals, so various signals we know very well: control signals, data signal, address signals. Okay, so if we combine, so in case of 8085 you will find 16 number of address lines or address signal, 8 did not to receive 8 data signals. So if we group the data lines or address lines or control signals, then at that time the group of signals are known as the bus signals. So here we can able to see the valid state where the valid data is considered. So here TR indicates the rise time, and during the falling time it is also known as the fall time, TF. Okay, so if we superimpose the signals, address signals, data signals, okay, so at that time you will find this kind of signal or bus signal. The next category, multiple line with high impedance. So multiple lines are having 3 states where logic 0, logic 1 or tri-state condition. So here we can able to see here in between two valid states, tri-state condition, okay, or high impedance state. Next one is the single line single effect. So in this case the change in one signal causes the change in the another signal. So status of one signal depends on the status of another signal. So in this waveform or timing diagram we can able to see three single line signals are there. So here the first single line is changing from logic 1 to logic 0. So due to this reason the second single line is changing from logic 0 to logic 1. Again here the first single line is changing from logic 0 to logic 1. Okay, so at the time of the rise time the third single line signal is changing logic 1 to logic 0. Okay, so the third single line signal is changing its state because of the change in the single line status, that is logic 0 to logic 1. So this is nothing but single line single effect. Then multiple line single effect signal. So in this case the change in the multiple signals causes the change in the other single signal. Okay, so here the status of one signal depends on, or change of state of single signal depends on change of state of multiple signals. So in this diagram we can able to see again three single line signals, single line 1, 2 and 3 supports. So due to the change in the two single lines, so here the logic 1 is changing to logic 0, and in the second logic 0 to logic 1. So due to the change in the both signal, the third single line signal is changing from logic 1 to logic 0. Okay, so this is nothing but multiple line single effect signal. So after this signal representation we will move towards the instruction cycle and machine cycles. Okay, so to draw the timing diagrams for the instruction, you should know various machine cycles which are observed with 8085 microprocessor. Okay, so as we know all operations are performed sequentially with reference to the digital clock signal. This you know very well, and each clock cycle is called as T state. So the number of T states required to perform an operation is called machine cycle, or simply we can say that the group of T states to perform the operation is known as machine cycle. And the number of machine cycles required to fetch and execute an instruction is called instruction cycle. Okay. So here in this diagram we can able to see, so here T1, T2, T3, T4, T5, T6, these are the clock cycles or T states. Okay, so the group of T states or clock cycles are nothing but machine cycles. So here M1, M2, M3, M4, M5 are the machine cycle. Okay, so group of T state is nothing but machine cycle, and the group of machine cycles is nothing but one complete instruction cycle. Okay, so under this instruction cycle, multiple machine cycle to perform the operation or to execute the instruction, that is M1, M2, M3, M4, M5 depending on the type of the instruction. And under this machine cycle, under this M1, you will find T1, T2, T3, T4, T5 clock cycles or clock period or T states. Okay, so simply we can say that the group of T state is nothing but machine cycle, and the group of machine cycle is nothing but complete instruction cycle. So now we will move towards the various machine cycles of 8085. The first machine cycle which is observed in every timing diagram, that is opcode fetch cycle. So this opcode fetch cycle is mainly utilized to fetch the opcode from the memory, or to take or to read the opcode from the memory. Operand fetch cycle, so depending on the contents available in the operand field, already we have discussed the instruction format which consists of opcode field and operand field. Okay, so in the operand field, if suppose the 8-bit or 16-bit address, so at that time operand fetch cycle is mainly used to read the data from the memory or from the register. Sometimes in the operand field you will find the 16-bit address, like the previous example LDA C000. So LDA C000 means load accumulator direct from memory location C000. So in the operand field we are having C000 16-bit address. Okay, and the operation of this instruction is to read the data from the memory. Okay, so to read the data from the memory, 8085 requires memory read cycle. If suppose processor want to store a data from accumulator to memory, for example STA C100, listen again, STA C100. So STA means store accumulator content directly in the memory location C100, that is data writing process, that is memory writing operation. Okay, so here 8085 requires memory write machine cycle. In the same way, IO read cycle, IO read machine cycle. Like memory read, IO read. Suppose processor want to read the data from the input peripheral, for example suppose keyboard, mouse or joystick. Okay, so at that time he requires IO read machine cycle. And opposite to this IO write, if suppose processor want to send a data to output peripheral, for example LED display, 7 segment display, LCD display, relay, okay, so at that time IO write machine cycle he will use. Interrupt acknowledge cycle, so during the interrupt, this particular interrupt acknowledge cycle get utilized. And ideal machine cycles, so ideal machine cycle depends on the type of the operation performed by the 8085 microprocessor. In the instruction set, some instructions are there like double addition. Okay, so double addition requires more time to perform 16-bit addition. Okay, so DADRP instruction we have already discussed. So this particular instruction to perform a 16-bit addition, and as we know 8085 is the 8-bit microprocessor. Okay, so as the DADRP for the 16-bit addition, so this 8085 requires more time for the execution. So at that time ideal machine cycles are internally used by the processor. So we will go one by one once again. So opcode fetch cycle. So here address of the opcode located in memory is given to program counter. Okay, so role of the program counter in 8085 microprocessor we know very well. So program counter helps to read or to maintain the sequence during the execution. So this is always the first machine cycle of any instruction cycle, that is opcode fetch machine cycle. So in this cycle opcode is taken from the memory and transferred to the instruction register for decoding, and the required time to complete the opcode fetch machine cycle is 4 T state or 6 T states, or 4 clock cycles to 6 clock cycles depending on the instruction. Then operand fetch cycle or operand fetch machine cycle. So this operand fetch cycle where the number of operand fetch cycles depends on the instruction size. The size of the instruction, how to calculate the size of the instruction we have already discussed. Okay, so typically instruction format you know very well, which consists of opcode field and operand field. Okay, so opcode field definitely we will 8085 requires 1 byte for opcode, and depending on the contents available in the operand, the size of the instruction may get changed. So for a 2-byte instruction it requires 1 operand fetch cycle. So for 2-byte instruction means first byte is always for opcode and another byte for operand. In case of 3-byte instruction, okay, it requires 2 operand fetch cycles. Okay, 1 byte, first byte for opcode and another 2 bytes for the operand. So here address of the operand is given by program counter. So the contents which are available in the operand are transferred to temporary register, not in the instruction register. Okay, in the instruction register always you will find the first byte of the instruction, that is opcode, and the required time to complete this operand fetch cycle is 3 clock cycles or 3 T states. Then memory read cycle. So as I told, the memory read cycle or this particular machine cycle is to read the data from memory. So 8085 executes this cycle to read the data from the memory. So in this case, address of data which is available in the memory is given by instruction, not program counter. Okay, so one instruction that we have already discussed, LDAC 000. So load accumulator direct from memory. Okay, location C000. So data which is available in the memory location C000 get loaded in accumulator. Okay, so in the operand field you will find the 16-bit memory location or 16-bit address of the memory location. Okay, so the instruction will give the information about the data which is available in the memory. So during this particular cycle, the signal IO/M bar made 0 by 8085. Opposite this memory write. So suppose processor want to store a data in the memory. Okay, for example, the instruction as I told a few minutes before, STA C100. STA C100. So STA means store accumulator content directly in the memory location C100. Okay, storing means data writing operation, data storing operation in the memory. Okay, so at that time 8085 executes this memory write machine cycle. So in this case also the address of data is given by the instruction, or address you will find in the operand field. During this case or during this particular machine cycle, IO/M bar made low. IO read cycle to read the data from the input peripheral or input device. So 8085 executes this cycle to read the data from input device. So in 8085 the instruction to read the data from the input device is in 8-bit port address. Listen again, in 8-bit port address. Okay, so the IO related instruction we will discuss in detail in the IO peripheral interfacing. Okay, so two main instructions are need to consider in case of IO, that is in and out. Okay, so in instruction to read the data from the input peripheral, and out 8-bit address, out instruction to send a data to the output device or output peripheral. Okay, so here the port address of data is given by instruction. So during this cycle you will find IO/M bar equal to 1. Then IO write. Okay, so 8085 executes this cycle to send or to write a data to the output device. Okay, and in this case also the instruction will give the port address. Okay, and during this particular IO write machine cycle, IO/M bar, you will find logic 1. Then interrupt acknowledge cycle, 8085 execute this cycle in response to the interrupt request input, that is INTR, to read the data from the interrupting device. Okay, and in this case the IO/M bar signal you will find logic 1. And finally ideal machine cycle. So 8085 execute this particular cycle for internal execution. Okay, so during this cycle all data, address and control lines are tri-stated. So 8085 doesn't perform any external operation. Okay, so some instructions does not complete their execution in given time period, like the DAD instruction that we have discussed a few minutes before. Okay, so those instructions require ideal machine cycle to complete the execution of the instruction. So this is the summary of the machine cycles. Okay, so in this table, the various signals, number of clock cycles and control signals which are mainly observed during the machine cycles. So opcode phase cycle. So during the opcode phase cycle, IO/M bar you will find 0. Status signal S1 and S0 both are 1 1. Number of T states or clock cycles required are 4, and the control signal read bar made low by the 8085 microprocessor. So RD bar equal to 0. Memory read machine cycle. So here IO/M bar is logic 0, S1 is 1, H0 is 0. 3 T states are required. Read bar signal equal to 0. Memory write. So here IO/M bar again 0, S1 is 0, H0 is 1. 3 T states are required, and here the control signal WR bar is used to write a data in the memory. IO read machine cycle. So here IO/M bar you will find logic 1, S1 is 1, H0 is 0. 3 clock cycles or 3 T states are required. Read bar made low by the processor during this particular IO read clock cycle, machine cycle. Then IO write. So here IO/M bar 1, S1 is 0, H0 is 1. 3 clock cycles, WR bar equal to 0. And finally interrupt acknowledge cycle. Where the IO/M bar equal to 1, S1 and S0 both are 1 1. 3 states, 3 T states. Okay, and INTA bar you will find logic 0. So this is the first machine cycle or timing diagram for the first machine cycle, that is opcode fetch cycle. Okay, so first we will see the various signals in this particular timing diagram, and then we will move one by one T state wise. Okay, so here T1, T2, T3, T4, these are the T states or clock cycles. Okay, or simply we can say that 4 T state opcode fetch cycle, and T5, T6 if we consider T5 and T6 clock period or clock cycle or T state. So here 6 T state opcode fetch cycle is also shown. Okay, so T1, T2, T3, these are the T states in this opcode fetch machine cycle. CLK is the clock signal. Okay, CLK is the clock signal. A8 to A15. So this is the higher order address. 8085 consists of 16 number of address lines, A0 to A15. Okay, and out of A0 to A15, A0 to A7 address lines are multiplexed with D0 to D7. This you know very well. Okay, so AD0 to AD7 multiplexed address and data lines, and A8 to A15 address lines are non-multiplexed. Okay, so A8 to A15 are higher order address lines, and A0 to A7 multiplexed with D0 to D7 lower order address line. Okay, so A8 to A15 higher order address bus. Okay, so group of address lines. D0 to D7 and A0 to A7 group of lower order address lines and group of data lines or data signals. Okay, so this is nothing but the address bus A0 to A7 or data bus D0 to D7. ALE is the address latch enable. Okay, so ALE signal is required to demultiplex address lines with data lines. Okay, so demultiplexing concept we have already discussed. Okay, how the A0 to A7 lines get separated from D0 to D7 by using latch IC. Okay, IC 74373 latch IC with ALE signal. Okay, so ALE signal to demultiplex address and data lines. IO/M bar signal, read bar and write bar control signals, and two status signals S0 and S1. Okay, so we will go T state wise. Okay, so the things which are happening during the each T state, that is during T1 state, during T2 state, T3 state, T4 state. Okay, so in T1 state or in the first clock cycle, 8085 sends the status signals S0 and S1 equal to 1 and 1. Okay, so here 8085 sends the status signals S0 and S1 both are 1 1 and IO/M bar equal to 0, which indicates memory related operation. So IO/M bar means IO related operation. If suppose IO/M bar equal to 1, that means IO related operation. So right now IO/M bar equal to 0. So M bar, okay, so IO/M bar equal to 0 means memory related operation. Okay, so this indicates opcode fetch or opcode fetching operation. Then the 16-bit address of opcode which is available in the memory. Okay, so here program counter higher PCH placed on A8 to A15. Okay, PC higher placed on A8 to A15, and program counter lower or address lower order address of program counter placed on AD0 to AD7 and remain only for T1 state. Okay, so PC higher, program counter higher placed on A8 to A15. Okay, and lower order address of program counter placed on AD0 to AD7, and this particular program counter lower remain only for T1 state. Okay, only remain for the T1 state. Okay, in the T2 state it is not there. Look here, in the T2 state PC lower contents are not there. Okay, because of the short duration ALE pulse, address latch enable pulse goes high to indicate contents of AD0 to AD7 as an address. Okay, so the address which is available on AD0 to AD7 get locked or get latched in latch IC. Okay, and then the same lines AD0 to AD7 same lines are used for opcode reading or for data transmission or data reception purpose. Okay, so now in this case the same lines, okay, same lines are used for opcode fetching. Okay, so ALE short duration ALE signal or ALE pulse goes high, and due to this reason the PC lower content get latched or get locked in latch IC, and same lines AD0 to AD7 lines are used for opcode fetching. Then in T2 state look here in the T2 state, the PC higher contents are as it is, but PC lower contents are not available in the T2 state. So in the T2 state, PC lower disappears on 80 to 87 and same lines are used as data lines. Okay, so in T2 state, the control signal read bar goes to logic 1 to logic 0, okay, to read or to fetch the opcode from the memory. So the opcode sent by the memory device to internal data bus D0 to DS1. Okay, so in this particular T2 state, read bar signal goes to logic 0 and the memory IC or memory device or memory chip which is connected to the 8085 microprocessor will send a opcode to 8085 data bus D0 to D7. Okay, so in the T2 state we can able to see here. Okay, so here the opcode fetching or opcode reading operation. Okay, and after reading or after loading the opcode in the internal data bus of 8085 microprocessor, the program counter get incremented by 1. Okay, so here you will find PC is equal to PC plus 1 means program counter get incremented by 1. And in the third T state, the opcode from memory transferred or opcode transmission from memory to 8085 microprocessor. Okay, 8085 microprocessor to instruction register, and in the T3 state, the read bar signal which is made active low in T2 state goes to active high, or memory device will make this read bar signal active high to indicate opcode sending or opcode fetching is over. Then in the fourth T state, 8085 performs internal operation. Okay, so in this particular period, the processor decides whether to move towards the T5, T6 state or the next machine cycle. Okay, that is opcode get decoded and decided whether it should enter in 5th or 6th T state or not. Okay, so if next byte or operand is present, next byte or operand is present means if suppose 2-byte instruction, 2-byte instruction, for example, suppose MVI A, 11x, MVI A, 11x. Okay, so this is 2-byte instruction. So MVI A, its opcode is 3E. Okay, and 11x is one more byte, that is 8-bit immediate data. So size of the instruction is 2-byte. Okay, so in the operand field, 8-bit immediate data is available. Okay, so at that time, if suppose next byte or operand is available, then it enters in operand fetch cycle to complete instruction fetching. Okay, if doesn't require T5 and T6 state, it will go to next machine cycle. Then about T5 and T6 T state. So utilization of these T states depending on the instruction size and requirement to complete decoding and some internal operations of 8085. So examples of the instruction with internal operation. So INX RP. So INX RP means increment the register pair, the contents of register pair by 1. Okay, so here due to the register pair it requires internal operation. Like this DCX, decrement register pair content. Okay, So incrementation of the register pair, decrementation of the register pair require more time. Then PCHL, load program counter with HL pair, call stack pointer decrementation by 1, return instruction stack pointer incrementation by 1. So these are the few examples where the internal operation and T5 and T6 clock cycles are required. So this is the complete opcode fetch machine cycle, 4 T state and 6 T state opcode fetch machine cycle. Then operand or memory read machine cycle. There is slight difference in operand fetch and memory read, okay, but timing diagram is same. So it is used to fetch the operand in multi-byte instruction, okay, multi-byte instruction, or to read data from memory, okay. So in operand fetch, address of memory location is given by program counter. How program counter? So suppose you have written the program and the first instruction in the program is MVI A11X, okay. So during the execution, the address of the first byte of the instruction get loaded in program counter. Why program counter? That we have already discussed, okay. So for sequential execution, program counter holds the address of the instruction, okay. So suppose this particular MVI A instruction gets stored in the memory, okay. So starting from C000, okay. So at location C000 in the memory you will find its opcode, that is 3E hex, okay, and next byte is 11x, 8-bit immediate number 11x. So size of the instruction is 2 byte, 1 byte for this MVI A opcode, that is 3E, and 1 more byte for this 11x, okay. So to store this particular MVI A 11x instruction we require 2 memory locations, okay. So first memory location suppose C000 and second memory location C001, okay, and during the execution of the instruction this address C000 get loaded in program counter. Program counter holds the address of the instruction, okay. So for sequential execution program counter plays an important role, okay. So in case of operand fetch, address of the memory location is given by program counter, okay. So here in the operand field we are having 11x and its address is given by program counter. Then about the memory read, so in this case address is given by the instruction, okay. So in this MVI A 11x in the operand field we are having 8-bit immediate data. Data is available in the operand field, but sometimes the data you will find in memory, okay. Now in this case we are taking 11x immediately in the accumulator, okay. In the operand field we are having 8-bit immediate number, but in the second case LDAC100 data is available in the memory, okay, and its address is given by the instruction. Which instruction? LDA instruction. LDA in the operand field we are having the 16-bit address C1000 where the data is available, okay. So LDA means load accumulator direct from a memory, that is memory reading operation, okay. So here the data is available in the memory, not in the operand field, Okay, so data which is available in the memory, its address is given by the instruction. So LDA, data reading or memory reading operation. So suppose this LDA C100 instruction is stored in the memory, so it requires 3 memory location. Why 3 memory location? Because this is the 3-byte instruction. How 3-byte instruction? 1 byte for opcode. Okay, its opcode is 3A hex, and 2 byte for the operand content. In the operand field C100, that is 16-bit address, that is 2 more byte. Okay, so always remember 8085 fetches the lower byte first, that is 00, and next higher byte, that is C1. Okay, so to store this particular instruction we require 3 memory locations, C000, C001 and C002. Okay, so in case of memory read, the address of data is given by the instruction. Okay, and it requires 3 T states for the operation. So this is the complete timing diagram for the operand fetch or memory read machine cycle. Okay, so once again here T1, T2, T3, these are the clock cycles. Okay, so clock signal, higher order address, AD0 to AD7 multiplexed address and data lines, ALE signal, IO/M bar signal, read bar, write bar control signals, and status signals H0 and S1. So in this case you will find H0 equal to 0 and S1 equal to 1 for memory read. So in the T1 state, 8085 sends the signals IO/M bar equal to 0. So IO/M bar 0 means memory device related operation or memory related operation. H0 equal to 0 and S1 equal to 1, which indicates memory read operation. The 16-bit address transferred on A8 to 15 and AD0 to AD7. In the operand phase cycle, the address is given by the program counter and then incremented by 1. So in this timing diagram we can able to see the higher order address placed on A8 to 15 and lower order address placed on AD0 to AD7. The short duration pulse goes high to demultiplex address and data lines. Okay, so in memory read, address is given by instruction, so it may be from register pair or stack pointer, or in the operand field you will find the 16-bit address. And the short duration ALE pulse, ALE signal goes high in this particular T1 state to demultiplex address lines with data lines. Then in T2 state, 8085 uses the D0 to D7 demultiplexed address and data lines for data transfer. Then the control signal read bar made 0 to read the data from the memory. So in the T2 state we can able to see here the read bar signal made low, that is logic 1 to logic 0. Then memory device sends the data byte on data bus of 8085, that is D0 to D7. So data from memory IC or memory device to 8-bit data bus of 8085 microprocessor. Then in T3 state, data from memory is transferred to 8085 and placed on internal data bus, that is D0 to D7. Next machine cycle is memory write machine cycle. 8085 microprocessor utilizes this machine cycle during the writing the data in the memory. So here in this diagram we can able to see the first 2 states in the machine cycle. So we will go T state wise. So in the first T state, in the T1 T state, like the previous timing diagram, 8085 sends the signals IO slash M bar equal to 0, H0 equal to 1 and S1 equal to 0, which indicates memory write machine cycle, or these signals get controlled by 8085 microprocessor. Then as usual, the 16-bit address of memory location transferred on A8 to A15, that is higher order address provided by the instruction placed on A8 to A15, and lower order address is placed on AD0 to AD7, that is multiplexed address and data lines. Then the short duration ALE signal goes high in this T1 state to latch the contents available on A0 to A7 in latch IC. So ALE signal goes high in this particular T1 T state. Then in the second T state, T2 state, A0 to A7 address signals get removed and same lines are used for data transfer, that is the data from 8085 microprocessor to memory IC. And then the control signal WR bar made low by the processor to write a data byte in the memory. So there is a printing mistake here. So here WR bar indicates data writing operation, not data read operation. Okay, so WR bar made 0 by the 8085 microprocessor to write a data in the memory. Then in the third T state, last T state, the data from 8085 microprocessor data bus transfer to memory IC or memory device. So here in this timing diagram we can able to see in T2 state the WR bar control signal made low by the microprocessor. There is no any change in the state of read bar signal because this is the machine cycle for data writing operation. So WR bar made low by the microprocessor. Okay, and finally after the data transmission in between the T2 and T3 state, so here we can able to see on AD0 to AD7 after demultiplexing the data from CPU or data from microprocessor get transferred to memory device. Okay, and in T3 state this control signal WR bar made high by the memory device, which indicates memory device has received the data from microprocessor. So this is about the memory write machine cycle.